All right, what can I help you with tonight?
I wanted to get back into some of the things we were talking about with the on-to, one-to-one, and I think there were maybe a few other points that I missed, but just some review on that, I guess,
Sure,
and preparation for the final.
that's right. Okay, so let's just review the definitions. Um, a function, onto, and one-to-one, especially the definition of function versus the definition of one-to-one. They look kind of similar. Um, so the definition of a function, um, a subset F of a cross product of two sets, A cross B, is a function from A to B.
I have a quick question.
Sure,
Why is it called a subset of the function if we're only talking about the two sets and everything that can be in them?
because we're not talking about everything that can be in them. Um, it is a subset of A cross B. Let's take a look in just a sec here. That's a really good question because what's going on with this A and this B? We'll look at an example of an A cross B, and then we'll look at some functions from A to B that are subsets of A cross B that qualify as functions. Generally, all of A cross B won't be a function unless A is only a singleton set and B is only a singleton set. I'll show you what I mean. Is a function from A to B, and it's denoted by this nice notation that is reserved for functions. We say f from A to B if each x in A, which is the domain, is paired with exactly one y in B, and B is the codomain. The ordered pair xy is in F if f of x equals y. Okay, so let's look at an example. If A only had one element, okay, and B only had one element, say 2, then A cross B is going to be all the ordered pairs that have a first coordinate coming from A and a second coordinate coming from B, right? How,
Right.
how many ordered pairs would there be in A cross B for this A and this B?
One.
There would just be one. It happens that this is a function from A to B because there's one element in A, namely the number 1, and there's one element in B, namely the number 2, and 1 maps to 2 if we call this the function f. Okay? The minute we have more elements in the codomain than the domain, then all of A cross B won't be a function. It'll be breaking the definition. Let's say B's got 2 elements, 2 and 3, okay? Here, F, which is just that single ordered pair, is a function, okay? But that's just because there's only one element in each of the domain and codomain. But what if the codomain has, well, what if B has 2 elements? What is A cross B in example 2? How many elements will be in A cross B?
It'll be two elements. It'll be 1, comma 2 and 1, comma 3.
Right. So this,
Oh,
see, this is A cross B, but it is not a function from A to
oh,
B because the element 1 is pairing up with two different elements from the codomain B, and that is exactly a bad thing.
oh.
This is so when we say F equals this set of ordered pairs, this is not a function from A to B. But we can take a subset of A cross B. So let's consider the subset G of A cross B, where G is just one or the other of these, okay? Let's take 1 and 3. That is a subset of A cross B, is it not?
Yeah.
And notice G is a function from
Hmm.
A to B because the single element that's in A only actually pairs with one element in B. So that is a function.
Hmm.
We could have taken the subset that just had the pair 1, 2 in it, and that would have been a function as well. So this is
Hmm.
not a function, but this is a function, and it's a one-to-one function because no element of the codomain appears more than once as a second coordinate, but it's not onto because the element 2 in the codomain is not paired up with any element from the domain. It doesn't have a preimage.
Oh.
Okay, so the game, can get more interesting. Let's say that A has two elements. Let's say A's got 1 and 2 in it, and B has 3 and 4 in it. A cross B is not a function.
Hmm. Oh.
What, 1, 3, 1, 4. What are the elements in A cross B?
1, comma 3,
Uh-huh, thank you.
1, comma 4,
Right,
2, comma 3, and 2, comma 4.
right.
Oh, that's
It's
interesting.
not a function though, because we would
Well,
be having two images for each of these elements of A, and that's not allowed. It's okay it'd be okay if 1 mapped to 3 and 2 mapped to 3. That would be a function, but that's not what's happening here. 1 maps to both 3 and 4, and 2 maps to both 3 and 4. So, you know, if F equals, A cross B, I won't rewrite it. I'll just say if we take all 4 of these ordered pairs, this is not a function
hmm.
because we've got elements from the domain A pairing up with more than one element of the codomain. So this is not a function. But we could take subsets of A cross B and build functions. As long as we take one of the ordered pairs that has 1 as a first coordinate and one of the ordered pairs that has 2 as a first coordinate, we can build different functions from A to B for this A and this B, but we have to make sure that no element from A pairs with more than one element of B. So if we just take a look, let's see if we can build every different function that is possible from this A to this B. Let's find all possible functions. From A to B. Okay. All right. So we'll call the first one F1. We're taking subsets of A cross B, but we have to be careful how we pick, right? So we could say, hey, 1 maps to 3 and 2 maps to 3. That's definitely a function because each element of A, namely 1 and 2, pairs with exactly one element in the codomain. They both happen to pair with 3. That's fine. This is a function. I think I want to put it in green. This is a function. It's not onto because 4 was not the image of either domain element. It's not 1-to-1 either because both 1 and 2 map to 3. So it's not 1-to-1. It's not onto, but it is a function. Let's just notice F1 is not onto because 4 is in B, but the inverse image of 4 is the empty set. There's nothing that maps to 4. Remember this notation, the inverse image?
I remember that.
F1 is not 1-to-1 because 1 is not equal to 2. These are two different elements, but F1 of 1 is equal to F1 of 2. They're both hitting 3. So when two different elements map to the same codomain image, that's what breaks 1-to-oneness. Let's just recall the definition. We'll get back to this and build the rest of them, but let's just recall the definitions of 1-to-1 and onto. A function f from A to B is onto if the range of f is all of B. In other words, it is each y in B is the image of at least one x in A. In other words, each y in B appears at least once as a second coordinate of an ordered pair in F. So this is not onto because there's a y in B, namely 4, that doesn't appear at least once as a second coordinate of any element or any ordered pair in F. And then the definition of 1-to-1 says that each y in B appears at most once as a second coordinate of an ordered pair. A function f from A to B is one-to-one. It's an if-then definition. We can look at both the if-then definition and the interpretation in terms of ordered pairs. If f of x1 equals f of x2, then that actually means x1 is equal to x2 back in A, i.e. each y in B appears at most once as a second coordinate of an ordered pair in F. And this first example here, 3 appears more than once as a second coordinate. In other words, f of 1 is equal to f of 2 because f of 1 is 3 and f of 2 is 3, right? F is mapping this way. But 1 is not equal to 2. So 1 is our x1, 2 is our x2, f of x1 is 3, f of x2 is 3, but 1 and 2 aren't the same element over here in the domain. So this function, it is a function, but it's not onto because 4 didn't get hit with an arrow, and it's not one-to-one because 2 different domain elements mapped to the same codomain element. Now, if we want to keep looking to find the rest of the functions from this A to this B, well, we could send both 1 and 2 to 4. That would be a function from A to B. 1 maps to some element, and it only maps to one element, namely 4, and 2 maps to some element, namely 4. It is a function, but it's not one-to-one, and it's not onto for the same reason that this one wasn't one-to-one or onto, except here in this function f2, both 1 and 2 would be mapping to 4. But there are a couple of other functions. We could say, oh, well, let's let 1 map to 3, and let's let 2 map to 4. Let's draw that picture. Well, this function is onto, isn't it?
Yeah, I think it's one-to-one too.
It certainly is. So this is a function, and it is onto, and it is one-to-one because it's onto because each element of B does appear at least once as a second coordinate in some ordered pair, and it is one-to-one because each element of B appears at most once as a second coordinate. There's one more function from A to B, from this A that has 1 and 2 in it, and this B that has 3 and 4 in it that is a function. What would that be?
I think it would be 1 to 4 and 2 to 3.
Yeah, and it would be one-to-one and onto. But there are subsets of A cross B that aren't functions, right? Well, we've already looked at all of A cross B. Technically, it's a subset of itself, and it's not a function. But, let's just look at one more kind of look at this particular set, because it's so easy when there's just a couple of elements, and then we can up the ante. Here's a subset of A cross B that is not a function from A to B. I'm going to call this subset C. What if we just say 1 is going to map to 3?
Um,
See? What's going wrong there?
it looks like a function. Oh wait, well, it's okay. It's got all the values, 1 to 3. Okay, so not all of the values in the domain have an image,
That,
and then, but okay, yeah, that makes it not a function because
that,
all of the domain values have to have images.
that's right. That's right. The element 2 in A does not have an image under image in set B. So it's not a function. That's another way that a subset of A cross B can fail to be a function. Here's another subset. We'll call that one C1. C2, well, let's make sure every element has an image. One has an image. It's actually got 2 images though. 2 has an image. And it's not a function because 1 has 2 different images. So these are the 2 fundamental ways that a subset of A cross B can fail to be a function. One way it can fail to be a function is if one of the domain elements doesn't have an arrow coming out of it at all. Another way it can fail is if one of the domain elements has more than one arrow coming out of it. And that's no good. Those are kind of the 2 fundamental ways that a subset of A cross B can fail to be a function. They are both subsets of A cross B, but they're not functions.
That's really interesting.
Yeah, it's nice when we can see a picture. Let's take a look at some infinite functions and ask some questions. Consider this function, the mod2 function. It has Z for its domain, and it maps elements of Z to either 0 or 1. The integers that map to 0 are going to be the integers that leave a remainder of 0 when they're divided by 2. In other words, where f of n is equal to n mod 2. In other words, you drop in an integer to this function. I like to think of functions as little machines. And you drop in a domain element, and then you crank on it. Deep, 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 and out comes the image, f of n. But here, f of n is whatever the remainder is when we divide n by 2. So in other words, f of 2 and f of 0 and f of, say, -4 would all be the same value, and f of 1 and f of 3 and f of -5 would all be the same value. What would f of 2 be?
0?
Yeah. And what would f of 0 be?
That would be 0.
Yeah. And all the
And
evens, right, give you a remainder of 0 when you drop them in to the mod 2 function. And what would f of 1 and f of 3 and f of -5 be?
they'd all be 1?
Yes, they would. So here's a question. Is f onto?
Ooh. No.
Well, let's take a look at what the codomain is.
Oh,
We're mapping from a big set Z into a teeny tiny set that just has 2 elements, right? And Z's got the evens. There's a bunch of evens in here. Easter time. And then here's the odds, and there's a bunch of odd numbers. And all the evens hit 0, right?
wow.
And all the odds hit 1. So it's definitely onto, yes.
Wow.
F inverse of 0 is all of 2Z, and that is not the empty set. And the inverse image of 1 is the odds, and that is certainly not empty. Okay. If you look backwards and you say, hey, is there anything back there that's going to hit 1? Oh, yeah. Is there anything back there that's going to hit 0? Oh, yeah.
Wow.
Is it 1 to 1?
No.
It's almost as far away from 1 to 1 as you could get. Not quite. The only way to get further away from being 1 to 1 would be if the domain was an uncountably infinite set. But you're right. It's no, because f of 2 is equal to f of 4, right? They're both hitting 0. For example, there's a gazillion different examples, but 2 is not 4. So in other words, f of x1 equals f of x2, but x1 is not equal to x2.
Just really quickly, so with that notation, x1 is not equal to x2. Does that mean that if they were equal, okay, because if they were equal, it wouldn't be a problem. It would be the same number mapped to the same number twice.
Right. It would say like f of 2 equals f of 2. That's not
Okay,
a
okay,
problem. It's only a problem when you've got different domain elements hitting the same codomain element. A problem
okay.
in terms of one-to-oneness.
I see. And that's just how they express it or write it.
It's
Okay.
it's the right, right. We need some kind of definition that will work. So let's take a look at the classic function uh, that's got a graph that's a line. All right, so let's say f is going to map from the reals to the reals, and let's say f of n, actually I'll say x because it's reals. F of x equals, say, 2x plus 3, okay? So if we graph that, it's just a line that has slope of 2 and y-intercept 3. I'm going to make this 2, this 4. And this, see, so when x is 0, y is 3. When x is 2, what is y?
7.
Okay,
Oh,
so
did
it's
I?
up here at 7. So there's our line. And it's definitely onto, because if you pick any y value, let's say, the y values are, here on the up down axis, the x values are on the horizontal axis. But if you pick any y in the codomain, we can find an x that will map to that y.
Hmm.
Just think about it. We want y to equal 2x plus 3, right? Where y is, some value like there. Well, you just solve for the x that will hit that y. Just, solve for x. So y minus 3 is 2x. Divide both sides by 2. The x that will hit y will be y minus 3 divided by 2. So over here we say, now here's our little proof that y is on, f is onto. Just pick y from the codomain, and then we cook up this x. Consider x equals y minus 3 over 2. We just double check that this x does live in the domain. Remember, when we check existence properties, we check that the object that we cook up that it exists in the correct set, in the correct domain. Remember when we were cooking up primes, we had to just double check that we were cooking up primes for our example or whatever. Well,
That's right. I remember.
right. So consider this x. Notice x is in the reals, and I'm talking about, the domain. Whereas when we took a y out of the reals, we're thinking about this copy of the reals, the codomain. We just want to find an x that hits this y. And then we just go through the algebra. What is f of this x? F of this x is f of y minus 3 over 2. Well, f is the function that doubles whatever we drop in and then adds 3. So we double this and we add 3. Well, the 2's cancel and we have y minus 3 plus 3. Oh, then the minus 3 and the plus 3 cancel and it hits y. Okay. So there is an x that maps to y for any y in the codomain R. We can always find an x that will hit it. And this f is also 1-to-1. If you pick any two different x values like x1 here and x2 there, or they could even be much closer together, but whenever you pick two different domain values, they map to different codomain values. They'll never map to the same thing. So the claim is f is 1-to-1. Let's just remember our definition of 1-to-1. Definition says if f of x1 equals f of x2, then that forces x1 to equal x2. Whereas the definition of onto is for all y in the codomain B, there exists an x in A such that f of x equals y. That was, that's the definition of onto, is that no matter what y you pick, you can find an x that exists such that that x maps to the y. Here's our definition of one-to-one. So to prove one-to-oneness, we're proving an if-then definition. Here we were proving the existence of the preimage x in A. We gave ourselves a y in B, and we found the x that exists in the reals that such that f of that x is y. Here, to prove that this definition is satisfied, we assume f of x1 equals f of x2. We assume the hypothesis, and then what we wish to do is show that x1 equals x2. Well, the definition of f of x is that, f of x is the function that doubles whatever you drop in and then adds 3. So f of x1 is 2x1 plus 3. F of x2 is 2x2 plus 3. And now we've got an equation, and we can just subtract 3 from both sides, right? And we get that 2x1 equals 2x2. And then you can divide both sides by 2, and you get that x1 equals x2. So linear
Right.
functions are always one-to-one. This proof works whether it's onto or not. So this very same equation will yield a function that's not onto, it'll always be one-to-one, if we change the domain from the reals to the integers. Let's look at that.
Can I ask a quick question?
Yes, of course, sorry.
What if you were to divide the reals into positives and negatives?
You could build a
With
function where you map all the positives to one image and all the negatives to one image.
oh, like we did with the other one. Okay.
Uh-huh. If you wanted to do that, you could sure do that. Yeah, there are lots of functions from the reals into little finite sets. Let's take this same f, but let's change the domain and the codomain. This is one of the WebAssign problems. All right, so f is going to be mapping from z to the z, and it's defined by f of n equals 2n plus 3. So it's the same equation, but it's a different domain and a different codomain. It's going to be z and z instead of the reals and the reals. So I'm going to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It helps to have graph paper. But we can draw. The interesting thing about this is that the graph, it's not a line. It's not continuous because there's space between the integers. So there's going to be space between the points on this function. All right, so you help me. When n, we can make the, the little chart over here, n and then f of n, right?
Mm-hmm.
When n is 0, what's f of n?
3,
All right, so 0, 3. That's a point on this function. When n is 1, what's f of n?
5,
Okay, so when n is 1, we're up to 5. But see, there's a big gap in there. There's a gap in there. All right, when f is 2, when n is 2, what is f of n?
7,
All right, all right. So 2 up to 7. You see what's going on? And when n is -1, what is
1.
uh-huh?
So when we're graphing and we plot points and then draw the line through, it's because we're using real numbers?
Yeah, it's because we have a continuous domain,
Hmm.
when it's Z, which is a discrete set, there's literally, space between the integers in a way that we don't have space between real numbers. I mean, you have space between two particular real numbers, but given any two real numbers, there are an infinite number of real numbers between them. But that's not the case. And this isn't perfect, but you can see that uh, if we look at these values, you can just look at these codum, these range values. These values in the second column are the range values. Uh, let's do one more. When n is -3, what is f of n?
-3.
Do you notice anything about all these images?
Uh, and um, I'm not seeing the pattern.
Okay,
3, 5, 7, 1,
I'm going to put
-3.
-2 here. When n is -2, f of n is -1. When n is -3, f of n is -3. So we've got some even values, but what are
Hmm.
all these?
They're the positives and negatives of the same values.
Well, 0, 3, 1, 5, 2, 7. Not quite, but do you see any even images?
Yeah. Um,
Oh, really?
I don't see repeat. Would you ask it again?
Uh-huh. Do you see any even numbers in the range?
Oh no.
That's right. There aren't
Ah,
any even numbers in the range. Look at this expression. Think about it. What this function does is it takes an integer n and doubles it. Okay, so right there, 2n is even, right? But then we add 3 to an even number. When we add 3 to an even number, what kind of number do we always get?
we get an odd number.
That's right. So the
Ah,
only values that drop out of, this little function, if we think about it, you know, you know, f of n equals 2n plus 3. Doesn't matter what you drop in there, what comes out is always going to be odd
hmm.
because of the definition of the function. And since this is mapping from z to z, we're only getting odds out. We're not getting everything in between. And that means it's not onto, it's still one to one. It's still, there's no two X values that hit the same Y value. It's still one to one. The proof of one to oneness that we used for the continuous domain and codomain still holds. If you set f of x1 equal to f of x2, you still have 2x1 plus 3 equals 2x2 plus 3, and you still can cancel the 3's and subtract, and cancel the 2's and get x1 equals x2. That still works. But this argument about onto doesn't work because this isn't necessarily going to be an integer.
Oh,
F is
uh,
not onto. And we can give a counterexample. Remember, onto means for all x in the domain, there exists a y. Oh, wait a minute. Got this wrong. For all y in the codomain, there exists an x in the domain such that f of x is y. That's the definition of onto. So the negation would be that there is some y, right? We just take the negation of this doubly quantified statement, right? So what's the negation of for all?
Exists.
And we keep the same set. So there exists a Y in the codomain such that
Such that, yeah, it becomes for all because it's the
for all
negation.
X in the domain,
F of X is not equal to Y.
that's right. In other words, we can find a Y in the
Hmm.
codomain Z. There's going to be a Y in here, in the codomain, such that no matter what X we pick from the domain Z, that X will not map to Y. F of X will not be Y. And so, we can show F is not onto by giving a counterexample to the claim that for all Y, we can find an X. We can find a Y that exists for which no X will work.
Hmm.
So, what did we just notice about the Y's that come out of this function?
They're all odd.
So, what do you think we should pick for a Y that we're going to be able to use to show that this F is not onto?
Any even number.
Yeah, so
Hmm.
consider what's your favorite even
Let's use
number.
two.
Okay, consider Y equal 2. We will show no X maps to Y equals 2. Okay, so if there were such an X that mapped to 2, right? We can do it by contradiction. If if some X in Z maps to Y equal 2, then that means, of course, the function is 2x plus 3. That means 2x plus 3, which, f of x would be 2x plus 3, and it would be equaling 2, right?
Yeah.
So 2x plus 3 equals 2. And now we can solve for x to see what x would look like. See, subtract 3 from both sides, and then what would x have to be?
Negative 1 over 2, which is not an integer. Wait. Yeah,
Exactly.
yeah.
So no integer can hit y equal 2 because it would take
Hmm.
negative 1/2 to hit y equal 2. And that's just because of that space that's existing between the image points.
That is really cool.
So you can, the fact of the matter is, if the line is mapping from Z to Z and this slope is anything other than 1, there'll be enough space in between consecutive points that you'll be able to find a Y you can't hit. Like if this slope is 1, you'll be able to hit every integer because, these go up by ones and you'll be able to hit every integer. But if this slope is 2 or 3 or 5 or -6, if the magnitude of the slope is greater than 1, there'll be enough space between the points that there will be integers y that you can't map to.
Wow.
There's some really, let me show you something fun, just because I think you'll appreciate it. There's something called the power set
Hmm.
of a set. Here's our definition. Given a set A, the power set of A and it's denoted by like a curly P. of A. Okay. Is, de is defined as follows. You'll like this. The power set of A is the set of B such that B is a subset of A.
Wow.
So the power set of A is the set of all subsets of A. All right. So if we look at the singleton set A, it's just got one element, let's find the power set of A. Okay. Well, A is a subset of itself, right? But there's another set that's a subset of every single set. That's
That's the complement?
the empty set is a subset of every single set. Remember the definition of subset. X is a subset of Y means if little x is in X, then the element little x is in Y, right? That's what it means for big X to be a subset of big Y. So I claim that the empty set is a subset of Y for any set Y. Why? Because it satisfies the definition. If X is an element of the empty set, then X is an element of Y. Why is that true?
Because the empty set is an element in Y?
It's a subset of Y,
Oh, oh, oh.
but it's a subset of Y. You remember the definition of subset.
Uh-huh.
You know, that's the way we proved subset inclusion. We took an element little x from set X and we proved that that element lived in set Y. Remember how we chased elements?
Yes.
All right, well, this if-then definition of subset is true when the set X is the empty set because what do we know about an if-then statement when the hypothesis is false?
We can prove a contradiction.
Yeah, I mean when the, when the when we have an if-then statement that has a false hypothesis,
Oh, that means that the conclusion is true by false positive. Was it false?
the if-then statement is true, not the conclusion necessarily, but the
Oh,
if-then statement is true by false hypothesis.
wow.
Remember that?
I remember that, yeah.
Well, guess what? When we apply this basic notion of logic to the definition of empty set being a subset of Y, there is no X in the empty set. This is always false. So this if-then statement is always true by false hypothesis. And that's why the empty set is a subset of every set Y.
Wow.
Because if X is in the empty set, then X is in Y. Yeah, that's right, because there is no X in the empty set. So the first thing, when we think about power sets, sets of all subsets, the empty set is always a subset of A. And of course, A is a subset of A. So the power set of this A has two sets in it. The empty set, because that's always a subset of A, no matter what A is, and A itself. But we can play this game, you know, you can keep playing and looking, you know, at slightly bigger sets like B, find the power set. We're looking for the set of all subsets of B. Well, it's just easy if you kind of just do it by starting with the smallest subset of B and working your way up to the biggest subset of B. B is a set. The empty set is a subset of every set, including this particular set that we're looking at that we're calling B. So the empty set is the smallest subset. What are some other subsets of B?
One would be just the element one, and then just the element two, and then one, two should be a
Mm-hmm.
subset. Okay.
Or we could even just call it B if we didn't want to write, 5 symbols. We could just say B. Yeah, this is the power set of B. And you can play games where we define a function based on a set and its power set. So let's just give ourselves, I'll just leave you this food for thought. Let's give ourselves a set with 3 elements. We'll call it A. We're going to define a function f from the power set of A into Z as follows. F of B is equal to the number of elements in B for every B in the power set of A. So what this function does is it looks at the subsets of A, look at each one of them one by one, call it B when you're looking at it, and it maps B to the integers that tells you how big B is.
So that would be like a count or a length method in a programming.
Yeah, it's a measuring
Ah.
function. F of B is equal to, there are a couple different notations for the size of B. Sometimes people just put the absolute value around B, or another notation for the size of a set is N of B
Mm.
equal the size of B, or N of B. And you can ask yourself questions like, is this function onto? Is this function one-to-one?
Um, well, it's the actual value it's producing is a count or the length. So I'm assuming it's getting bigger or smaller depending on the values going into it.
Right, depending upon the B that you drop in to the function, the size of B will be different for different subsets B of the set A. But A only has 3 elements.
So you'll start with one element because that's a subset. So like one in a set and then two. Okay, so right then it would have one element, but then it would have another, it would have a count of one, but then it would have another count of one because it would have three counts of one because each of the
Uh-huh.
individual elements would be
Good.
subsets.
So what do you conclude about one of the properties?
It is not one to one,
That's
and it is
right.
onto.
Can you hit 100?
Oh, no. Mm.
So, however, so it's not one-to-one, and we can't hit big elements of Z, right? But if we defined G the same way, power set of A into the set 0, 1, 2, 3, where A is this set that's got just three elements, where G of B is the size of B, then this would be on to.
Would the empty set match to zero? Because,
Because the
okay.
size of the empty set is 0 because the empty set has 0 elements.
Ah, cool.
Now you could play the game a little bit bigger and you could just let A be the integers and it's the same function F, but now we're going to go from the power set of Z, which is our A, into 0, 1, 2, 3, dot, 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 where F of B is the size of B for all subsets B of Z. In other words, for all B in the power set of Z. Is this F onto? And I think you've already answered 1 to 1, but you could just think about it.
I think that it is onto because it's the entirety of the set of integers mapped to counts
That's,
that are,
mhm.
yeah, I think it's onto.
That's right, because no matter what integer n you're trying to hit over here, you could just build a subset of Z that has that many elements in it.
Right. Yeah.
Like,
And you could hit the infinite set, you could quantify with infinity. So yeah, it's
I
onto.
don't think you need to do that because honestly, to hit all of these, you just need to hit each of them with one set. So it, see what I mean? Like Z is a subset of itself. Oh, wait a minute. Is this a well-defined function?
Huh?
Oh, we're gonna have to, oh my gosh. Here we're gonna have to have another option because if you're looking at the subset of Z, that's an infinite subset, like all the evens is a subset of Z, right?
Uh-huh.
And the size of that set isn't any finite number. We have to include this possibility as one of the codomain elements that we reserve for the subsets of Z, the B's that are infinite subsets. And we got to include that.
Well,
Oh, you made me a little smarter tonight. Thank you.
well. So it's onto, and I would assume it's 1 to 1 too, because and a certain count is only going to have a certain value.
Oh, careful.
Oh,
You already figured out, even for A equals the set containing 1, 2, and 3, you already figured out
oh, that's right. Oh,
that
that's right.
right, because you said, hey, the subset that just has 1 in it is going to map to 1, and the subset that contains just 2 is going to map to 1. So,
Oh, that's right.
right, and that problem is here in spades, isn't it?
Wow. That's absolutely, yeah, wow.
It's
That's
hard to
really cool.
Isn't it? It's hard to imagine try to visualize all the different subsets of it's not so hard to imagine all the subsets of Z that have one element. Like we can see them kind of. And we might even kind of start to see all the subsets of Z that have two elements in them, you know? I mean, it could be any two integers. There's a whole bunch of ways to build a subset of size 2, right?
Hmm.
But then when you start thinking about, okay, I'd like to get my head around all the subsets of Z that have 100 elements in them, or What does a subset of Z look like that has an infinite number of elements in it? How many
Wow.
of those are there? There are an infinite number of them.
Wow.
Like 2Z, isn't that a subset of Z? The evens? That's an infinite subset of Z, right? But what about 3Z? Every third integer, right? All the multiples of 3, remember those? When we are
Uh,
dividing by 3? There's a bunch of subsets, that kind of go along with that, but certainly this one is an infinite subset of Z. But what if we're dividing by 4? We could grab one of those subsets. What if we're dividing by 5? All the multiples of 5, that's an infinite subset of Z, right? You could play that game ad nauseum. And that's not the only way to build an infinite subset of Z. It was like you were saying, what if we took all the positive reals and then took all the negative reals? Yeah, you could do that with Z too. You could take all the positive integers, you know, and call that a subset of Z. Take all the negative integers. That's a subset of Z that's infinite.
wow.
So these are just games that set theorists like to play just to have fun. I hope that I addressed the main questions that were concerning you.
Absolutely. Just some practice and to see how you describe it, because that's something that's a little challenging. On tests, I have to put it into words what I'm looking at.
Oh, I
So,
can, yes. And yes, that is the hard part, isn't it? But
yeah.
that's what you're learning to do. That's what you're learning to do.
Yeah, this was really helpful. I appreciate it.
You're very welcome. I enjoyed it. All right, well, we'll see you soon.
All right. We have class Tuesday and Thursday, and
Tuesday.
then
Finals,
just Tuesday.
yeah, finals
Okay.
start Wednesday.
Okay. Okay. All right. Okay, then I'll see you Tuesday, hopefully.
Yeah, you should look at your finals schedule, Nora.
Okay.
Like for all
Yeah.
your classes, you should start laying out I'm sure you've done that, but
Oh
that's
yeah, yeah.
that's this week.
I have my dates right now in front of me. I thought the discrete math final was this Saturday.
It is.
Okay. All right. So our last class is Tuesday, and then we have our study time, and then 3 o'clock Saturday.
That's right.
Okay. All right. Okay. Thank you.
You're welcome. Good night.
Good night. Take care.